Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're happy to have David Sontag here from Nextdoor. And he is going to talk about approximate inference in graphical models using LP relaxations.
Thank you for inviting me here. So many of the problems that we need to solve in machine learning and related fields are modeling problems. So for example, in protein folding, we need models that are capable of allowing us to take a newly discovered protein sequence and predict its structure. In computer vision, we would like models that can help us understand what is an image about, how far are the objects that are present in the image, what action is taking place. In systems biology, we'd like to take the results of high-throughput protein-protein interaction experiments and knockout experiments and use these to predict what regulatory networks are present. In information retrieval, we need models that can make sense of documents. So how can we extract relevant information from a document, such as advertising keywords? Or so graphical models, which will be the focus of this talk today, give us a powerful means of specifying prior information about the structure of the problems that we're working with. And these models then allow us to make predictions, such as the ones I've talked about. So the next couple of slides, I'll go into the top two applications in some more detail. And then I'll return at the very end of the talk to the application I mentioned in systems biology. And although I won't talk about it today, I am working quite a bit on these information retrieval problems, and I'd be happy to talk to you guys about it later. So we'll start out with a problem in protein folding, which is going to then motivate a lot of the rest of the talk. So suppose we're given some new protein sequence. So for example, there's a lot of sequencing going on down the street here at the Broad Institute and Whitehead Institute. And suppose that we knew part of the structure of that resulting protein. So let's say we knew the backbone structure. And the goal was to predict the global folding of the protein. So we want to go from something like this to something like this. So how do we do that? Well, one way to try to do that is to construct a model for the problem. So one example model, which is displayed on the right there, would say, okay, we're going to first discretize the side chains, which are these quantities that protrude from the backbone structure, into let's say one of 100 possible states, referring to different angles that side chain could be in relative to the backbone structure. The discretization here is actually a very smart discretization, which makes use of a large database of previously.
Wouldn't it also have to say what the side chain was, and not just what angle it's at relative, or would what it is tell you what angles it could be at?
So we start
a little picture next to
yeah.
the
Okay.
Yeah. Or what's that little picture?
So we start out with so graphical models involve graphs. So that's the first thing here, right? So a lot of people hear the word graphical model and they think of computer graphics, but no computer graphics here. The graphical refers to graphs. So what we do is we say, okay, there's some random variables of interest here. In this case, the variables are the particular locations of each of the side chains. We know what the side chains are, we just don't know what angle they are in. And then we want to construct a graph, which really captures what the structure of the problem is. So in this case, the graph structure is given to us by the backbone, which we already know, or we're assuming that we know. So the backbone will tell us, well, the side chain at this location is physically close to the side chain at this location. And so we may want to put in some prior knowledge about coming from physics or chemistry. For example, saying that the angle that this is in.
Graph, then?
So not necessarily a complete graph, because
It doesn't look like it, and yet if I wanted to know how close that X1 was to the bottom guy, how would I do that?
No, close is not.
Oh, close is not, the length of the edges there is not
So each-
physically close?
so the So the nodes in the graph refer to the variables of interest. The edges refer to what constraints we're going to put onto the problem.
Okay.
So we don't necessarily need constraints between every pair of variables, but for example, we would care very much that two sidechains that are physically close to each other should not ever be in a location, should not ever be in a rotation which overlaps, right?
Okay.
And there might also be, so in general, there are going to be attractive and repulsive forces which we're going to want to model here. But there is a lot of locality, so things that are very far away, there is not going to be, we may not care to model the repulsive forces there because they're simply never going to be present.
Okay.
So the arcs that are connecting these blue dots have something to do with the geometry, but not that much.
They have something to the geometry, but more at a high level. Yeah. So in particular, for each edge in the graph, we're going to define so that the model will define a real valued potential function, which is going to be defined over every pair of states that the two variables could be in. So for example, it'll say, suppose x1 will refer to a discretized state, so some particular angle that sidechain is in, and x3 refers to another angle of the other sidechain. And this potential function would be negative infinity if these two sidechains were ever overlapping, so touching each other, which is not physically realizable.
But then as they get close, would you have like some very strong,
A very strong potential function, yeah, repulsive function.
So it's one real valued thing which is anywhere from minus infinity.
Ever from minus infinity to positive infinity, yes.
And
You
minus
have to
infinity.
code that up using your knowledge of chemistry or whatever.
Yeah, so where do these come from? That's a very good question. So sometimes they're learned from data. And that's a very interesting question, which I won't talk about today, but I'll mention it at the end of my talk. But these are typically actually used, constructed from background knowledge. So a physicist or a chemist will come and say, well, these are the actual repulsive forces that are present, coming from physical knowledge, and that's how those are generally constructed.
This has as an implicit assumption that the backbone itself doesn't matter, right? Because this theta 1,3 is just a function of x1 and x3, doesn't seem to be a function of the backbone in there. And yet, if I had those two same side chains on a different backbone, even if they were the same distance apart on a different backbone, they would probably be acting very differently.
So the backbone matters a huge amount.
Okay.
And so it
So I
shows
just
up in,
don't see that.
Yeah, so it shows up in two different ways.
Okay.
The first way it shows up is in terms of figuring out what is the correct model structure. So what edges did I draw down? There was actually a function. The edges I drew down were a function of the backbone.
Mm-hmm.
But the second part is we're also going to be modeling repulsive forces with respect to the backbone. And so typically you might see those represented as single node potential functions. So a function which depends just on x1 or a function that just depends on x3.
I see. So those are implicitly in there also.
So yeah, just for simplicity, I didn't draw those, but you could just subsume them into these.
Good.
It also matters, right, whether variable x3 and x1 actually care about the angle overlapping or not, depends where 3 and 1 are on the backbone.
Physically located on the backbone,
if
correct.
they're in far enough away so that they never could enfolding.
Right, and that's why he doesn't have some edges
So
there.
you make
Correct.
this
For
blue
those of us who
by
don't
hand.
know much about physics or biology, so is it important that we understand backbone and all that stuff, or is it just important that these are features, x1, x2, x3, just some representation of
X1 or x2 are not features, but they're random variables.
random variables, which are real numbers?
So I discretize them into, let's say, 100 discrete states.
Okay, so each discrete, and that's some representation of the thing on the left?
Correct. So this corresponds, some assignment to each of those variables will give you a picture that looks like this.
Oh, for the output on the left and bottom.
On bottom left, yes.
You make this blue graph up by hand, or you synthesize it automatically or semi-automatically from what's on the left?
So I synthesized it manually as a sketch only of this thing. Of this thing from this. Yeah. So I only drew edges where I would expect there to be an energy term.
So that means in reality, this graph has sort of 10,000 of nodes, and drawing it involves 5 Guardian student years?
No. So typically they involve roughly 100 to 200 nodes. regarding the number of amino acids that are in a protein.
Because you don't have that many side chains, right? I mean, each one of these is a side chain, right?
Correct.
Yeah.
And so typically these start out as a complete graph. And once you so the potential functions are really given to you by physics. Mm-hmm. And after you calculate what the potential function is between two pairs of side chains, you'll realize, well, it's so small it's negligible, so we just don't draw it there.
Okay. So the fact that you have a graphical model here, is it an approximation? So nodes that are not connected don't affect each other at all, or it just represents a very weak effect?
It's an approximation.
Oh, okay. And you.
So that is to say, everything.
Have, 3 nodes that somehow affect each other.
I'll answer both of those questions. I'll answer both of those questions. So first, as is everything with modeling, the model is always wrong. It's just an approximation. So why do we come up with models in the first place? Because it allows us to do things we couldn't do without them. Okay, so there's no question about it. The model is wrong. Right. Second question regarding what about higher order potentials, right?
Yes.
So the structural biology world is, for the most part now, just using these second order terms. So these, what I call pairwise potentials. Mm-hmm. However, there are a lot of other applications of graphical models that use higher order potentials. And the techniques I'll be talking about today are all applicable to those as well. But just going to, for simplicity purposes, just have pictures like this.
In physics also, most of the time, you just represent things as two-body potentials, even though, of course, technically they're not. But that's a very common assumption in physical models.
And you could actually map any higher order problem to one that looks like this as well.
Might be a good idea if we moved on to the next slide.
Yeah.
Yeah, no, it's okay.
We could
Actually,
spend another half hour on this slide easily.
we can move on, but I have relatively few slides, so we can have more discussion. So don't worry. Okay. Back to the story. All right. Okay. So we've got this graph. We want to get here. How do we go from point there to point here? Okay. So there's something missing, which is this. All right. So we formulated now a discrete problem, and to get to the prediction, we're going to do the discrete optimization. Mm-hmm. So what I'm showing to you here is I'm summing over the edges of the graph of, for each edge, the potential function. And now the prediction comes from finding the assignment to each of the variables, which maximizes this sum of potential functions.
So some of the variables were known and some weren't? Or?
None of them are known. So we want to predict a global assignment of sidechain angles to for this protein.
Now, what you've done, though, is you've taken what is, in reality, a continuous problem,
Yes?
made it a discrete problem.
Yes?
It's not going to be too hard to solve, so you're going to relax it, I would assume.
It's not going to be too hard to solve?
It is going to be
It
too
is
hard
too hard
to solve.
Yes.
So you're going to relax it.
Yes.
But then you're going to round at the end because you're using discrete variables, I would guess. And why are you not just dealing with continuous variables if you're going to set up an optimization problem and it comes from a continuous problem?
Very good question. So first, regarding the discretization, so these guys are really smart when they do the discretizations. So it's not some uniform discretization in terms of angles. They actually say, okay, well, let's look to see if all of the proteins we actually have their whole 3D structure. Let's find a protein which has this particular side chain and then a similar looking backbone. Mm-hmm. Let's figure out what angles can it actually be in relative to that side chain. So these are extremely smart discretizations using databases, first of all.
Okay.
But second of all, so a very big question is, well, a lot of real world problems are continuous problems. Mm-hmm. So there are 2 ways to go here. The first one is just try to solve it directly in the continuous domain. Mm-hmm. But you might ask, what is this, if you picture this as a continuous function,
Right.
What would it be? So you have to parameterize it somehow.
Uh-huh.
And typically these are very nonlinear functions.
Oh, yes.
So for these nonlinear functions, the discretization is actually a very nice way of representing it.
Okay.
So why do you believe that the protein is solving the hard problem?
Good question. So somehow you put this sequence at an extremely high level into some solvent, some solution, right? And this magically pops out. And so it's a very good question of, well, what is the process which allows it in vivo to do the folding? I'm not focusing on that today.
Can you step up? I'm sorry, but I think, so there's some experts here who probably understand exactly what you're saying, but I would feel like a lot of people who don't know what you're talking about. So there are these variables, right? This is this graph on the right is specialized for this one particular protein?
Yes.
So you would have to have a different graph for every different protein?
Yes.
And you construct maybe they're all based by hand or whatever, and then you solve this, and that's how you get the answer.
Yes.
And those potential layers are just arbitrary functions that they the things are.
That very smart people came up with.
It's a truth statement. Potential is a truth statement.
Let's go to the next example. And so first of all, this is the focus of the talk.
Okay.
And let's go to the next example, and then you could keep asking those questions. So I talked about applications in computer vision. Here's an extremely simple application in computer vision, which we're still doing very wrong, as Chet would be happy to tell us. Wherever he's sitting.
Is that one?
Yes.
Yeah.
There it is. Okay,
Sarah?
so we're given two images. So you can think of this as the image seen by your left eye and the image seen by your right eye. And the goal is to figure out what is the depth of the objects in the image. So this is called the stereo vision problem. So we want to take these two images input and output a depth map. So actually, the way we're going to really solve this is slightly different. We're going to say, well, for each pixel in your left eye's image, how far is that pixel moved in your right eye?
Mm-hmm.
Right? And then we can directly map actually, so the depth is the inverse, or something proportional to the inverse of that distance. So the more it's moved, the less far away it is.
Mm-hmm.
So the model for a problem like this would be, again, a graphical model, or this is an extremely simple model, where for each pixel in the left image, we have a variable which can take on states saying how far is that pixel dislocated in the right image. And we'll just assume that these two pictures are horizontal. So the dislocation are on the same level, so the dislocation will only be horizontal. And the potential functions for this type of problem will say the following. So an object, two pixels that are part of the same object are going to be dislocated roughly the same amount because they're the same distance from the viewer. So if two pixels look very similar, so for example, both pixels on this white face object, if they look very similar, then it's very likely that they're from the same object, so we would want them to be dislocated the same amount. If they look very different, they're probably from different objects, and so you would expect them to be dislocated different amounts. And so that's what these potential functions would represent. And again, right now, these potential functions are mostly specified by hand. And this is actually a very bad model. I'm not going to be talking about it for the rest of the talk because I'm very frustrated with this model. So we have good results on these types of problems. Good results in terms of we can solve the combinatorial optimization problem, great, but it gives you very bad predictions for how far away things are. So I'll just put that last thing there.
Can you say that about your biology application?
The biology application is one where actually this is the state of the art. Yeah. Adam.
You say specified by hand, I mean, they're really specifying some meta rule that will take into input two images, one image or two images, and
Two images.
output such a bunch of potential functions.
Right. So at the end of the day, so where this field is going is that those meta rules should be learned. But that's something I'll talk about at the end of the talk.
When you say the biology system is state of the art, do you mean it actually gives good predictions? Or do you mean that we don't have anything like the human vision system that's so much better to compare it to?
So I mean that it's useful. So these stereo vision models, as far as I know, and please correct me if I'm wrong, are not used in sort of robotic systems right now. On the other hand, the structural biology models I was showing on a previous slide are used on a daily basis by people working on protein design, for example. So
He's asking, are their standards just lower than
No, no.
the
so-
standards of people who have stereo vision and
Is it
can
as good
compare
as God
this?
in predicting the way?
No, no, no. I mean, there's a lot of no. It's not perfect by any means, but they're still useful. So So I'm working with a group at MIT right now who's trying to design better antibodies. So you care about, given an antibody, what is its binding affinity by varying some of the amino acids in this sequence and predicting what is the resulting structure. You can try to design a structure which is much more stable and results in higher binding affinity. And these things are actually using those types of energy models, right? And that is the state of the art. Yeah.
So actually, for stereo vision, this algorithm also is state of the art.
Can you say that?
It is a state of the art.
Oh,
it works really well if two images fall into the model, right? If your assumption is correct. But in real applications, that's not true, right? Because the two images are not that clean and many noise. Right? So the assumption actually breaks most of the time. That's why it's not using this kind of model for real stereo canons.
You mean the thetas will be wrong?
Okay, but so again, the focus of this talk is how do we do this optimization problem?
So you're saying if you generated the pixel image by computer, you would perfectly learn
More or less.
Any questions about the setup? Okay, so far I've told you we are solving these extremely hard optimization problems. Why? Because, well, basically every hard problem in combinatorial optimization that we know about, max cut, vertex cover, coloring, 3-sat, all of these things could be formulated in this form. Right, so this problem is clearly NP hard. Now, nonetheless, these models are very effective ways at formulating approaches to solving problems, and they're used everywhere right now in practice. We really do need fast algorithms for solving these optimization problems. They're often used as part of a larger system. For example, the stereo vision application you might want to have within a flying helicopter, which then needs to figure out what is the distance of objects that it's looking at so it can figure out how to avoid possible injury. So we need algorithms that are capable of doing this inference extremely quickly. The problems, as a general problem, it's inapproximable in almost every way. And regardless, if you were to come up with a new model, it's very easy to come up with new models, and there simply aren't enough theoreticians in the world to come up with good approximation algorithms for every new model. So what we really need are general techniques, is what I'm trying to motivate. So what people in the field actually do are heuristics. So they do local search, they do simulated annealing, and they also do something called max product belief propagation. So these heuristics are ways of trying to do that optimization that don't give any nice guarantees for optimality. So for example, given the output of one of these algorithms, you really don't know how good the solution is. And given the output, you really don't know, well, if it's bad, how can I try improving the results? So once local search converges to some solution, to some locally optimal solution, if it's a bad solution, what then? You could randomly initialize and start again, but that's basically it. So the approach which I'm going to be talking about today is a generic method of trying to solve optimization problems like this, but which uses linear programming relaxations. And in the process, I'm going to have to give some new results on these types of general optimization problems in order to enable the application of linear programming relaxations to these large-scale machine learning problems.
What's MAP?
So MAP is what I'm calling the globally optimum assignment. It comes from maximum a posteriori assignment.
So why do you mention all the time that this is a machine learning question? What's the learning? What are you trying to learn?
Very good question. So I say that because I call myself in machine learning. But what I really see this as is, so Okay, and also these things are published in NIPS and other machine learning conferences, right?
Okay.
But what I really see this is that these are computer science problems, right? And machine learning, in particular people who are working in probabilistic modeling, is sort of this natural middle way point between, say, theoreticians, like many of you in the audience, and people who are trying to actually apply these methods in practice. So the machine learning aspect is just thinking about what are the right models for these types of problems, what are generic algorithms for solving it, and they talk a lot with the actual people in applications. So a lot of people in machine learning straddle between, let's say, NIPS, which is a machine learning conference, and computer vision conferences or computational biology conferences and so on. And at the end of the day, what you really want to do is learn these functions and
Learn the thetas.
learn the thetas. So that will bring it back to a purely machine learning problem. Okay.
Wait, David, I have a question.
Yes.
What sorts of generative models is this capturing? I mean, is this an MAP question for? Is it like Markov random fields?
So what I'm writing up, so what I've talked to you about so far are Markov random fields. So they're graphical models on undirected graphs.
Okay.
There are also graphical models on directed graphs, which have a much better generative semantics. And I'll talk about that briefly at the end of the talk. But these things are not so different as they might seem. Okay, so first I'm going to start with the big picture of the approach. So what we're going to do is we're going to take this discrete optimization problem, and we're going to formulate it as an equivalent linear program. So what I'm drawing for you here is a polytope. In 2 dimensions is a polygon. So the extreme points, the vertices of this polytope, correspond to the assignments that we're trying to predict. So every possible sidechain position, or every possible assignment corresponding to different sidechain positions corresponds to one vertex on this polytope. If we were to be doing a discrete optimization problem, we would be searching over just the vertices. But instead what we're going to do is we're going to say, okay, let's take the convex hull of all of those vertices. Now we have a polytope, and we're going to maximize over this polytope. And since one of the maximums of this polytope will occur at an extreme point, it's an equivalent problem. So we haven't exactly made it any easier by turning this into a linear programming problem because
I don't quite understand. I mean, you seem to have sort of implicitly claimed that all your vertices are integer points.
Yes, I am, by definition.
Yeah,
Which is not in general the case for these linear programs. You could have half integer vertices.
No. So I'll get there in a second. But what I'm telling you is so this is what I'm calling the polyhedral approach. So first we take your discrete optimization problem and turn it into an exact linear program. Now that linear program is over a feasible space, the polytope, which has exponentially many extreme points and also exponentially many constraints.
So almost every assignment is going to be 1 point roughly?
Exactly every assignment. The assignments are 1-to-1 with the vertices.
How does it end up being linear if your theta j's aren't linear to start with? Are you assuming they're linear?
Yes, so I do some linearization, which I'll talk about next. So this is just a pictorial view of it. I'll get to the details in a moment.
They were supposed to be nonlinear.
Yeah. So I'll get to that in a second. Okay.
I have a question. So like usually when you just look at all the LP stuff, when you see exponentially many constraints, you are not that concerned because you can try to solve it like going to the dual. So why doesn't it work here?
No. So the reasons why you might not be.
What was his question? I missed it. Maybe you could repeat the question. Or
So if I understood correctly, you're saying you can often solve these things more efficiently, for example, in the dual, and so the exponential number of constraints isn't a problem.
Oh yeah. Sorry.
But that's not the case here. Yeah. So sometimes you have separation oracles for these constraints. Sometimes you can show that there's a lifting, which is equivalent. None of those things are true here, right? So this is an NP-hard optimization problem. If you had a compact representation for this polytope, you would have solved an NP-hard problem. So this is not going to be compact. Right? There are going to be exponentially many extreme points, exponentially many constraints. Okay, so the reason why I'm starting with this formulation is because at the end of the day, we want to solve something like this. But we're going to start out with something simpler. So first we'll start out with the relaxation of this problem, where we take your original polytope and we relax it by getting rid of most of the constraints. Now this relaxed problem is going to be much simpler, so we can describe it with only a few constraints, and it's going to include all of the integral extreme points. So if you happen to find an integer solution, you know it's optimal. So the properties of the LP relaxation, first, since we're optimizing over a larger feasible space, the optimum value will only be bigger. So the LP relaxation gives you an upper bound on the globally optimum assignment, which I'm calling the map assignment. Second, and this is something that you need to prove, you can show that if the solution is integral, then it's exact. So this type of formulation gives you a certificate of optimality. If you get lucky, you solve the problem, and you get an integer solution, then you know you're done.
Assuming that theta is linear.
Yes, this is after the formulation. Yeah.
After the linearization.
After the linearization.
So it's an exact solution of the linearized problem.
The linearization is not the problem. It's an exact solution of the discrete problem.
Right. Okay. No.
So there are many different possible relaxations for any combinatorial optimization problem, and in general, how do you choose which relaxation to use? The goal should be to get a relaxation which is as tight as possible. So we want this. So if the objective is maximized here, we would like the blue region to be as close as possible to the red region near here. Right, so that's what the goal should be. But how do you get to that? Well, the general approach that I'm going to be using is to start with a very loose relaxation and then tighten it iteratively. So you guys might have heard of cutting plane algorithms. So the general approach will be to start with this and then say, okay, suppose the objective function points in this direction. The optimum solution might be here, to the relaxed problem. We're going to see that the relaxed problem is actually the relaxation is very loose near this optimum solution. So we're going to look for a constraint that we could add in. We add in that constraint, thereby making the relaxation a bit tighter in that region. Solve again, get a new solution, add a new constraint, and so on.
How do you know it's loose?
So because of the way we formulated the linear program, we know that the relaxation has integer extreme points and fractional extreme points. If you get an integer extreme point, because of the way we formulated it, we know it's within the correct feasible space. But if it's fractional, you know it's outside. So you have a very quick test. Is it a fractional solution or an integral solution?
But just because it's outside doesn't have to mean it's very loose. It could be.
How do you find the cutting plane?
Right. So I'll get to that in a second. So the solution here, in the very lucky case, is actually integral, and so you're done. But the key questions posed by this approach are, first, what are the valid constraints? What are the constraints that we can add in? And second, how do we efficiently find violated constraints? So both of you asked, what are the cutting planes? Right? What are these constraints we're adding in? Ideally, we want to add in constraints which make it as tight as possible. So these are the questions which I'm going to be addressing in this talk for this very general discrete optimization problem. And the underlying theme will also be, how do we make this approach practical for large-scale problems? So I really want to solve the problems that people in the graphical modeling community have.
And a large-scale problem has a few hundred variables or a few million?
Both. So I'm interested in both scales. Mm-hmm. So I really want techniques that are applicable to millions of variables.
Each of which has 100 discrete positions.
So that I don't know how to do yet. So I'm also going to claim the techniques I present actually work. And they're going to work in these two different regimes. One regime where you have not so many variables but very large state spaces, and the other one where you have a huge number of variables but the state spaces may not be too large. Okay, so the big picture here, it's one which all of you should be quite familiar with. It's a standard technique. Start with an integer linear program formulation, relax the integrality constraints, solve that linear program somehow. Then this is the part which is perhaps a bit newer. We're going to tighten the relaxation by adding in constraints, follow that circle many times, and then if we're lucky, we output an integer optimal solution. Otherwise, if we're not lucky, we might have to do some rounding at the end of the day to get a prediction. Okay, so I'm going to take you through each of these steps. So first, what is this linearization? How do you know when to stop? Good question. When you're out of time.
How many graduate student lifetimes?
But for the structural biology problem, surprisingly, what we're finding is we're actually getting integer solutions after not so many constraints. So once you get an integer solution, you can stop because that's optimal.
Provided you don't have an integer solution, can you stop? Do you have a...
So if you don't have an integer solution and you stop, then you have few guarantees. What you do know is that you can measure the integrality gap because you have your LP value and you have your integer solution value, and you can look at that gap, so that you know. If it turned out that your problem was a nice problem, such as max cut, you could also try to get some other guarantees from rounding, but generally you don't.
But I think maybe he's asking, like, would you even be able to convert those fractional numbers into some meaningful representation of the original problem?
Oh, we generally just do rounding, as is typical with LP relaxations. Okay, so now the linearization step, which a couple of you asked about. So we take this original formulation where the potential functions, these were functions of the possible states that these two variables were in, and we want to come up with a linear objective. And our way of doing that is to introduce new variables for each edge and each assignment to that edge. So we're calling these mu ij, which is defined on xi and xj. And intuitively, we want these to be 1 if that assignment holds and 0 otherwise. So, for example, if the variables were all binary, they can only take 2 states, then we've just introduced 4 times the number of edges variables. Okay, so now that we have these variables, the objective is clear. We're going to now maximize summing over the edges in the graph, summing over the possible assignments to each edge of this function, which is now since it's instantiated, it's just a real value, times that variable. Okay, so that's the linearization step. It's standard.
So I should think about this as being either a problem that has highly, I'm going to be fine as long as either it's got very few states and it's linear, but if I have a very nonlinear function, even if I have a small number of states, by the time I've completed the step, I've suddenly got a big problem again, right? So if those potential functions are very nonlinear, by the time I'm down here, I've suddenly got a big problem. Whereas I might have started with a small number of states.
So I'm assuming that we're starting with a discrete problem.
Right, so if it was discrete, if that number was, I guess there are only so many. Yeah, I guess maybe that's right. If it's small enough, there are not really that many.
There are exactly, so in the binary case, there are exactly 4 times e variables in your linear program, and if these take on k states, then you have k squared times e variables in your linear program.
It doesn't go that quickly.
No. Okay, so what are the constraints? So just for simplicity, I'm going to introduce some extra variables that aren't necessarily needed. And the variables are going to be for each node, so not pair of nodes, but for each individual node, it's going to be intuitively 1 if that variable takes on that state or otherwise. Okay, so the first constraint is just an assignment constraint. Straightforward. We want this to really be an indicator variable, so we want it to be only 1 for 1 assignment. The second constraint is saying that we want that the edge variables are consistent with the single node variables. So if an edge variable, if a single node variable, let's say for I is 1 for xi equals 0, then we want this edge variable to be 1 for whatever, it doesn't matter what xj is, but for any value of xj, it should be 1 only when xi is equal to 0. So if we sum this over all possible values that xj can take, it should be equal to mu I xi.
Hey, I just wanted to point out this is actually the earth mover relaxation. I'm not sure if people in the audience might be more familiar with that, but this is
the basic LP relaxation for most combinatorial optimization problems. So it goes by other names as well, not just that. This is a very common formulation. And then finally, the integrality constraint. So it's easy to show that this is an exact integer linear program for the discrete optimization problem. Okay, and now we do the standard thing of...
Do you make any assumptions on the thetas?
No.
On the costs? None
No.
whatsoever?
None.
They don't satisfy triangle inequalities?
Absolutely not. Actually, absolutely not. And that's what makes this so hard, right?
Okay.
So if they had satisfied triangle inequalities, if they were all positive, then we could hope for some, nice approximation algorithms. But none of those things apply in these real-world problems. Okay, so now we're going to relax the problem, and I'm going to call this the pairwise LP relaxation. I'm calling it pairwise because it involves these edge variables, which involve two things, pair of things. So the relaxation simply takes the integrality constraint and tosses it out and replaces it with a bound constraint, saying that these variables should be between 0 and 1. So this is the starting place for a lot of different combinatorial optimization problems. Okay. So let's move on to the other details. So first, how do you solve this linear program? There are lots of ways of solving linear programs. There are interior point methods, there are simplex methods, dual simplex methods, and so on. We are going to work in the dual linear program. So just give you a sketch here. So the primal...
Previous slide, you said that you have exponentially many constraints and you didn't.
No. So you have... So, good question. This integer linear program is equivalent to the first polyhedral formulation. So if you ignore the integrality constraint, it's only polynomial number of constraints. Now once you put in the integrality constraint, it implicitly puts a huge number of other constraints on the problem. That's where the exponential comes from. But once you relax it, now you have a linear program which is compact. It only has linear number of constraints. Okay, so we're going to solve the linear program in the dual. So the dual always upper bounds the primal linear program. And remember that your primal linear program was relaxation, so that itself, the optimum upper bounds the value of the map assignment. And the reason why we work in the dual is it gives us some nice properties. For example, any dual solution, regardless of whether you've solved it to optimality, gives us an upper bound on the value of the integer solution. So it allows us to measure this integrality gap.
So do you actually write your own solver?
Great question. Okay, so believe it or not, we do. So I'm not going to claim that this is the best approach to this problem. And in fact, I think there's a lot of work to be done here. But what we do is an extremely simple approach. We solve this dual linear program using coordinate descent. Now, why do we do it with coordinate descent? Well, first, it's extremely simple to implement. You can write...
Coordinate descent? So you fix a coordinate and you go down that?
So we're actually doing block coordinate descent. I'll go more into this later. But you choose a couple of coordinates. You fully optimize in that direction. You choose another couple of coordinates, fully optimize in that direction. That's coordinate descent. So we formulate the dual in such a way such that coordinate descent is really easy to do. So it's extremely simple to implement. And I say fast, and the reason I say fast is because we've actually run this on really large problems, and they solve it. And they solve it optimally and quickly. So it works.
So it works better than Cplex?
It works much better than Cplex.
That's so weird.
Yeah, it's really weird.
Do you have any idea of what in the structure of the program would make coordinate descent be a good method? Because that would tell you, it seems to me, a lot about the structure of the problem.
Yes. So I'll get back to that in a second.
Okay.
Okay, so just a little sketch on what is this coordinate descent. So this is the graph that we started with in the beginning, and I'm just going to show here a sketch of the dual objective decreasing with coordinate descent as well. So each coordinate descent operation is actually going to be choosing one of the edges of the graph, taking all of the dual variables that relate to that edge, and fully optimizing that edge. Then you're going to choose a new edge in the graph, do the same, and so on. So the coordinate descent steps are very local to the graph graph. Now, the algorithm actually looks extremely similar to max product belief propagation.
Yeah.
So I'm not going to go too much into max product belief propagation because it's not essential to this talk. But that is a heuristic which is used in machine learning to solve combinatorial optimization problems like this. And it doesn't typically give any nice guarantees, although some people, such as Jennifer and Christian, have worked on showing that max product does optimally solve the combinatorial optimization problem for some particular classes of problems, such as matching-based problems. But max product belief propagation doesn't have any guarantees in any other setting. It's basically just a heuristic. So the algorithm which we obtained by just doing coordinate descent looks just like max product. It has one additional term which makes a lot of sense. And it could also be interpreted, except it's derived in such a way that it's directly solving the dual linear programming of an LP relaxation. So we know exactly what it's doing. Okay. Why does this work so well? Good question. My suspicion is the reason it works well is because for these types of problems we have very strong local evidence. So for example, in the structural biology problem, we have some idea because of the backbone structure what angles are possible, which ones are more likely than others. And so by doing this local propagation, we have we start with a good prior and we propagate that prior in some sense.
Now, it also is that parallelizable?
Yes, it's extremely parallelizable.
Just like BP is.
Even more than BP
Even
is.
more.
The reason why it's more is because you can prove that the parallelizations are actually still solving the dual linear program. So for example, a simple way to parallelize this type of algorithm is you take a coloring of your graph and you do coordinate descent on disjoint regions. And each of those coordinate descent steps are valid coordinate descent steps and they don't interact with each other. So they all minimize the dual LP.
So you color the edges?
You color the edges, correct. Yeah. So these things are very parallelizable. And
Like that you can do for belief propagation.
what's that?
Something like that you can do for belief.
You can do the exact same thing for belief propagation, but you don't really know what it's going to do.
Except in very special.
Except in very special instances, yeah. Okay, but so I don't want to say that this is the approach for the future, but this is an approach that we found to be extremely effective, and it enables us to solve the linear programs when we're talking about sometimes millions of variables. So really large-scale problems because of basically because of the simplicity of the algorithm. Okay. So, and it has a lot of relationship to what people are currently doing in distributed optimization. For example, Baruch Auerbach has been working on distributed optimization algorithms that look very similar to this, but have nice guarantees. And I think there was a lot of room for future work on algorithms like these. Okay, but to get back to what this talk is really about, we solved LP relaxation somehow. I showed you how we're doing it in the previous talk. And now we need to tighten the relaxation. How do we do that? So there are many well-known approaches for tightening relaxations. So one of the most popular ones are lift and project approaches. So I think many of you are probably familiar with ones based on the STP relaxations, so the Lovász-Shriver and Lasserre relaxations. You guys are probably also familiar with Shradley-Adams hierarchy. So these are all very standard ways of taking a discrete optimization problem and lifting it via a series of rounds where you add more and more constraints with each round. So
is the one which, in practice when people do matchings, they actually, in many cases people use sort of one of these algorithms rather than interior point itself because it's not guaranteed to work, but in practice it works fast by adding these.
Why are you comparing it to interior point?
Well, maybe because if you do matchings, there are sort of algorithms which guarantee you sort of to find.
Oh, okay, sure.
Not interior point. So if you do matchings, there are sort of
combinatorial algorithms.
Combinatorial algorithms guarantee you to do it in polynomial time.
Yes.
But in practice, people actually do this kind of adding constraints
Yes.
to the integer program.
Yes.
And then it could theoretically run in exponential time, but in practice it never does.
Correct.
So how is yours related to those?
It's the same idea. Okay. So we are going to, our first approach, I'm going to give two approaches. The first approach uses the Shirley-Adams hierarchy. So, so I'll go more into what the constraints actually look like in the next slide. But here's the big distinction to what people typically do. When people typically start working with Shirley-Adams hierarchy, they say, okay, we do one lifting and we do another lifting, and each lifting corresponds to very big operations. They take so the first lifting would take every 3 nodes in the graph and put a constraint for one of those. So now you've turned a problem which was linear in the number of edges into something which is now cubic in the number of variables. And they're simply not applicable to these large-scale machine learning problems because even one lifting takes too much time. So in order to make these techniques practical, what we give is a technique for doing a partial lifting, where we only add some of the constraints between each round.
And how do you choose which one?
That's the topic of the talk.
And in principle, you could add sort of a 5th level constraint before you add a 2nd level constraint.
In principle, you could, yes. Okay, so what are these constraints? So the original LP relaxation, I'm only showing part of it here, has the linear objective, and then it had these consistency constraints, which it made sure that the edge variables were consistent with the single node variables. Now, the lifting will introduce a cluster involving some of the variables, and it'll exactly represent that cluster, and then it'll enforce consistency between that cluster and the original variables of your problem. So, for example, we could take these 3 nodes, x1, x2, and x3, introduce a new set of variables in the linear program defined over the cluster of 1, 2, and 3, and we have one variable for every assignment to those 3 nodes. Then what we're going to do is we're going to say, okay, these should sum to 1, which corresponds to choosing one assignment for those 3 nodes, and they should be consistent with the edge variables. So if you were to sum this cluster, these over x1 states, it should give you the same value as the edge variable 2 and 3. So I might be using slightly different vocabulary than the one that's typically used in papers about Shirley-Adams, but this is the Shirley-Adams lifting. But I talked to you about it with respect to one cluster. Okay, so the overall algorithm is now going to look like this. We're going to start by running coordinate descent on just the pairwise LP relaxation. Coordinate descent is decreasing the dual objective with each iteration. So I'm showing here, this is the map value. This is where we want to get to. We start out with some upper bound. Each operation is decreasing that upper bound.
Just to be clear, you don't know what the map value is.
We don't know what the map value is. Yes, it's just a sketch.
Because you talked about knowing the gap between them, but you actually don't.
You don't know the gap until you find it. Correct. You can get a bound on the gap, as you'll see in a second. So we run coordinate descent until we converge to some solution. That is to say, more coordinate descent steps aren't improving the dual. Then we attempt to decode an integer solution from the dual. So that is to say, we're working with the dual LP. We want to come up with a primal solution. So we do our best job at trying to come up with a primal solution. And the primal solution will be somewhere down here, which allows us to now evaluate that gap. So we don't know this number, but we do know this number. Now, the gap is large, so what do we try to do? What we now try to do is we say, okay, let's try to tighten the relaxation. So we look for a cluster, and the distinction here is we're not doing a whole round of lifting, we're only trying to do a partial lifting. So we look for one cluster to try to add to the relaxation. We choose a cluster, and I'll go into more details of how we choose in a second. We choose a cluster, and then we do, in the machine learning literature, we like to call it warm start. Basically, we take that new cluster, and we do a very smart initialization of the dual linear program, where we leave all of the other dual variables relating to the other edges fixed, and for the new cluster, the dual variables relating to this new cluster, we initialize smartly, so that we get immediately the same dual objective value that we had beforehand, and we can just keep on optimizing from there.
So the initial and smartly, you could just optimize over this one variable, right?
What do you mean?
Set of variables.
There's lots of
about these cluster variables, but that's not that many variables, so you could just.
Once he knows the cluster.
So basically what we want, so now that so once you add this new cluster constraint in, you have a new linear program. But you don't want to start optimizing this linear program at the beginning. You'd ideally like to be able to reuse all the work you've already done.
But what I'm saying is if you fix all your other dual variables, then you just have this few variables for your new cluster.
Yeah, you give those some value, and that gives you your initial solution.
But if I would, instead of having to be smart, I could just optimize over these few variables.
Coordinate descent over these variables.
And that's what the next step is going to be. So we start with some initialization. It turns out we do it such that we have the same dual objective. And then we start optimizing.
And
right?
which clusters do you choose?
He
Get to that in a
hasn't
second.
told us that yet. That's the.
Haven't told you that. I'm leaving you in suspense intentionally. Okay.
That's what I'm waiting for.
Okay. We keep learning coordinate descent. Again, we try to decode an integer solution. We see there's a gap. We choose a new cluster.
Wait, is it guaranteed that this other one is now higher? Maybe it's
No. It could certainly be lower. But you can still try to measure a gap using the best previous integer solution you found. You do, again, warm start. You continue optimizing, and so on. You continue this process until, if you're lucky, maybe you'll actually find the integer solution, which has the same value as your dual, and so you know is optimal, in which case you're done.
And
the
you're
reason you keep
assuming
telling us
it's.
if you're lucky is you actually have some experience with finding these integer solutions.
Yes. I'm using the word lucky because we don't have any proofs that this is going to work in general.
And what if
But
it's
for these
not
real-world
unique?
problems, we find that they do. Sorry,
What
what's
if it's not unique? I mean, you said you found the solution. What if? I
So-
mean, are you assuming that you're always dealing with cases? in
No.
which it's
And
unique?
in fact, often it's not unique.
Right.
And that causes real
And
problems.
then you're going to get like fractional solutions when you get mixtures of those.
So the decoding process, which I'm not talking to you about at all,
Mm-hmm.
is troublesome when the solution is not unique.
Right.
And so we have some methods for dealing with that, but I'm not going to talk about that today.
Okay.
I'm happy to talk to you more about it later. Okay. So I didn't lie to you. It actually looks like that. Okay. So this is the dual algorithm I just described applied to one of the real-world problems. Actually, I think this is one of the stereo vision problems. Okay. So the x-axis is as before. It's the number of iterations, each coordinate descent iteration. The y-axis, the top line is the dual objective. The bottom line is the decoded value. As you can see, it does go down on occasion. And eventually, we solve this problem optimally. Okay, you can't see the little jumps because there's a lot of iterations there.
This was roughly how many variables?
Maybe 10,000.
Each has how many discretizations?
16. It's a non-trivial problem.
How much time does this take?
I don't know. I think this was 1 hour on a MATLAB extremely slow implementation. So MATLAB is. We've since optimized these things. We released a C++ implementation that's on my webpage. You guys can download. It's very fast. Okay, so the key question. What cluster did you add next? Now, unfortunately, I don't have a very elegant solution to this. I have a very simple solution. So what we do is we do a greedy bound minimization algorithm. And this very strongly takes advantage of our having worked in the dual linear program. So what we do is we say, OK, let's do a one-step look ahead. Let's look at each of the clusters we could have added. And let's see if we had added this cluster and done just one coordinate descent step local to that cluster, so something that's very simple to evaluate, how much would the dual objective decrease? And then we choose the cluster which decreases the dual objective the most with that local, very greedy approach. Okay. So that is the very simple technique that we're using. But it works. And just a quick note, if it turned out that you're doing this operation when the dual objective was optimal, and you find a cluster such that the dual decreases, then that implies that the original primal LP relaxation was not tight. It's an obvious consequence of it. Okay, so let's try to apply that simple algorithm to a structural biology problem. Now, I'm actually going to tell you about one which is harder than the first one I talked about.
How many times do you need to do this?
Good question. I'll tell you in a second.
Okay.
Okay, so originally I told you about what's called sidechain placement. You're given a backbone structure, and you just need to figure out how are the sidechains going to be angled in the optimal solution. here I'm going to tell you about a much harder problem, one of protein design. So now we're given some target 3D structure, and we want to figure out...
I'm just going to say that we only have 10 minutes left, so you should know that, and also we should know that.
Oh, okay.
And kind of let you finish.
Oh, okay. Thank you for telling me. I'm going to speed up. Okay, it's a hard problem. Each state now corresponds to, in addition choosing the angle, choosing an amino acid. So we're designing a protein. Even after a lot of pruning, you have about 100 states per variable and sometimes up to 180 variables. So it's a very big, very hard problem. Also, this problem has very large tree width if you look at that graph. So you couldn't just use a dynamic programming approach to try to solve it. The primal linear program, even before you try adding any clusters, even before the first lifting, is very large. So we have on the order of millions of variables and hundreds of thousands of constraints. If you try throwing this thing at Cplex, it can only solve the 3 smallest proteins in our data set. And the dual algorithms are much more successful at solving these. Okay.
When you say Cplex, have you optimized the parameters of Cplex? I mean,
good question. No.
So Cplex is not one algorithm. There's many algorithms.
So
dual algorithms there.
So that part was done by some colleagues of mine, and they tried a lot of the different Cplex algorithms. So they tried dual simplex, primal simplex, interior point, and so on. They've tried all of them. They didn't. I don't believe they've tried tweaking the individual parameters in the interior point algorithm, if that's what you're asking.
I'm just surprised. I mean, these are standard LPs.
But they're very big.
Millions of variables is not very big in LP.
So I think there's a memory constraint. Interior point is very slow. It's cubic time with each operation. So I need to move on due to my time constraints. Sorry. Okay, so we applied this iterative...
We're tightening
the
constraint.
Yeah, sorry. So I'm going to speed up now. Okay, so we did this iterative tightening approach using... it turns out we only had to do one partial lifting. So we just used clusters over 3 variables in our tightening. And we found that using this approach allows us to solve 96 of the 97 proteins that we considered. When I say solve, I mean we actually found an integer solution. We also have a dual solution which has the same value, so we have a certificate of optimality. Right, this implies that there's no integrality gap for these instances, which we might find surprising given all of the results in theoretical computer science showing that one lifting doesn't improve our approximation guarantees, or even large number of liftings don't improve approximation guarantees. In this case, it does. Or sorry, for these instances.
How much time per instance?
So I'll get to that in a second. So the pairwise LP relaxation only solves 2 of the problems, so the lifting was really necessary. The greedy approach of choosing the clusters worked really well. In order to solve them optimally, we only had to add between 5 and 700 constraints out of tens of thousands of constraints. So we very smartly chose which constraints to add in. That answers your questions. How long does it take? It takes a long time. It takes like a day to solve each protein optimally. Now, a day in a protein design world is actually not that bad. That's standard.
A day on what?
A day to optimally solve one protein.
He's saying on what machine?
On a slow machine.
On a PC.
A PC, a very slow machine, single processor, so on. Yeah.
Oh.
Okay. So what's left to do? I'm going to get to the really interesting stuff now, or other interesting stuff. So let's consider the two regimes. The first regime is very few variables but large number of states. That's the example that we just saw. Another regime is many variables, small number of states. So in the first regime, we have the problem that even one cluster constraint could involve a huge amount of computation, because even though it's just one triangle, one triplet, if the state spaces are, let's say, 100 states, now you have 100 cubed operations to do each time you deal with that cluster. So that's the reason why it took 1 day. In the second regime, we have a different type of problem. The search problem is very hard. So, for example, if you had a very sparse graph but millions of nodes, you're not going to want to try every possible cluster within your greedy bound minimization algorithm. You want a much more efficient algorithm for finding the constraints to add in. So I'm going to tell you how to deal with both of these. To deal with the first problem, this is just one slide. we designed a new set of constraints which are sparser than the old constraints. So rather than using a full cluster constraint, we enforce consistency just on coarsened variables. So here's the pictorial representation of it. So this is your original edge variable, and this is the cluster constraint we're going to add in. It's only going to represent these coarse states. Then it's going to enforce consistency on the coarsened region. So these two should be consistent on this region. So these are going to be weaker constraints, but it turns out that they're still good enough to solve the protein design problem. And now we can solve them optimally. The largest problem is within just an hour and a half, again in a very slow MATLAB application. But this is an area where they measure time on days, so that's really quite a striking result. Now I'm going to go back to the second application. So the second question was, again, how do you find the constraints efficiently when you have, let's say, sparse graphs? So here we're going to bypass the lifting altogether. I'm going to give you a different approach. Now we're going to look directly for violated constraints. So the picture I gave you in the beginning of the talk where I added constraints one by one, but only a single linear constraint each time. So how do we do that? Well, can we use what's already known about the cut polytope? It turns out that for binary Markov random fields, when the variables involve just two states, the binary marginal polytope is equivalent to the cut polytope, which is studied with relation to the max cut problem. You guys might also have come across the cut polytope in studying L1 embeddability of metric spaces. So a lot is known about the cut polytope. So for example, everyone has looked at using triangle inequalities as constraints to tighten the relaxation, and so on. And so for binary problems, you could apply all of these techniques. And furthermore, for sparse graphs, in the operations research world, they found that these cycle inequalities are extremely useful. In fact, Barhone and Majub proved that for maximum cut on planar graphs, these cycle inequalities exactly define the cut polytope. So you can exactly solve max cut on planar graphs using these constraints. But there are exponentially many of them. So what they solved was how to find the most violated constraint in polynomial time using a shortest path algorithm. So you can exactly solve max cut using this separation algorithm. Right. But our problem isn't binary, not even close to being binary. The problems that the graphical models that I'm looking at all involve non-binary variables. So the question is, how can we use what's known about the cut polytope for our non-binary setting? So the way we do this is, our generalization to the non-binary setting uses the idea of projections. So we're going to take your marginal polytope on a non-binary problem, look at the cut polytope. We're going to project any point from the marginal polytope onto the cut polytope via linear projection. So I'm denoting mu as your non-binary problem, mu 1 as your binary problem, and the projection is given by a matrix pi. Okay?
So does this mean that you're approximating your cost function by an L1 metric?
So I'll get back to that later.
Okay.
Or talk to me about it later.
Okay.
Okay. So then what we do is, so what we're going to do is I'm going to tell you how to derive constraints for the marginal polytope from constraints we already know about for the cut polytope. So suppose we have a point in this polytope. We project it into a point here. And then suppose we find a constraint on the cut polytope. Now using that linear transformation, we can pull back that constraint to come up with a valid constraint for the marginal polytope. So we go from there to here. Right? And since it's a linear transformation and a linear constraint, this is all trivial. Right? So your constraint here is just going to be A transpose mu less than or equal to B. Now, since mu 1 is just pi mu, because it's a linear transformation, you pull it back and you get a new constraint for the marginal polytope, which is A transpose pi times mu is less than or equal to B. Okay. So how do we actually do it? What are those projections? So the simplest possible projection would be to take your non-binary problem and partition the state spaces so that you turn your non-binary problem into a binary problem. So for example, here I'm illustrating where xi is your non-binary problem, yi is your binary problem, and I'm showing you how I'm clustering the states of xi such that yi only involves two different states. So we'll just call this the new 0 and this the new 1. so this would be one way of trying to turn a non-binary problem into a binary problem. And in fact, it gives us a linear transformation, which I'm just going to illustrate for this one edge. So the new variable yi will be 1 whenever xi was 3. Similarly, yj will be 1 whenever xj was 0 or 3, and so on. So this is our linear transformation. And each choice of partitioning, each partitioning per node gives us a different linear transformation. So we have so suppose each node takes k states, you have 2 to the k to the n possible projections that we could get. So if each of those projections gives you now a binary problem, which you could then take any constraints known for that binary problem and pull it back to be valid constraints for the non-binary problem. Okay, now unfortunately those are quite a few constraints, right? So now I'm going to tell you about a quickly tell you about a technique for doing the same thing but much more efficiently. So the key idea is to, rather than projecting multiple times for each partition of the states, we're going to project just once onto a cut polytope corresponding to a much larger graph. In that way, we'll only have to do one projection instead of 2 to the k to the n possible projections. So let's define a projection graph. So I'm going to define for you the larger graph to have one node for each partition of the original variable. It's a very simple idea, but it's effective. So this is the original edge, and the new graph for that edge now has, for variable I, I'm going to have 3 new nodes for the original variable. For variable j, I'll have 7 new nodes for variable j. Each of the new nodes will correspond to a different partition. Okay, so you have a complete bipartite graph for each edge, but I'm only showing you the part of the graph. Okay, now the projection is actually done in the same way. So for each individual edge corresponds to one choice of partition here, one choice of partition here. That projection from this value is done as I showed you on the previous slide. And now using this new graph, which there's only one graph now, you can apply any of the separation algorithms that are known for the cut polytope, such as the cycle inequalities, and all of the constraints you could have gotten via this approach, you can now get from this approach. So now, rather than being polynomial in 2 to the nk, we're polynomial in n and 2 to the k. Okay? And furthermore, this is a very general technique where you don't have to go all the way to the full graph. You can start with just a subgraph. So you might, in practice, start with a smaller graph and then work your way up to bigger ones. And they're actually very smart heuristics that you could use to not have to use all possible partitions. You could rule some out. Okay, so in conclusion, I hope I've motivated that this is going to be an effective approach to approximate inference in graphical models. I personally believe that these approaches based on linear programming relaxations are going to replace max product and local search as the default tool used for inference in graphical models. And the reason why it's so nice is because using this approach, you get basically everything you had before, but more. You also get bounds and certificates of optimality, and using the linear programming relaxation, it allows us to use heuristics within a solid theoretical foundation. So there's no doubt about it. My particular scheme for optimizing the LP, my particular scheme for choosing what constraints to add in, all of these are heuristics, and there are many more heuristics. But because we're working within the dual linear program, we can judge the effect of each of these heuristics, and we have guidance at every step of the algorithm. So I think, I really do believe that these will be the techniques of the future. And these are widely applicable in machine learning. I'm not going to go into any details here. The talk is done. There are 2 slides more. I've applied these same techniques to the problem of learning Bayesian networks, so now learning the structure, where I'm not going to go into the details, but now rather than the marginal polytope, we've got something called the Bayesian network polytope, which is very closely related to the acyclic subgraph polytope, the linear ordering polytope, maximum spanning tree polytope. And we again applied the same technique, same polyhedral ideas to give one of the first global approaches for learning Bayesian networks. All of the previous ones were based on local search or Monte Carlo methods. Yep. And there are some interesting future directions, which I believe are, I'll just tell you two things. The first one, I find it very surprising that this works. Okay? Everything I know about from the TCS community tells me this shouldn't work. Right? A couple of liftings shouldn't allow us to optimally solve these problems. So why does it work? I think a really interesting question is to understand what is it about the structure of these problems that allows the linear programming relaxations to succeed with so few liftings? And the second question is how can we use these techniques now within a learning approach to learn the parameters of the model? Now, for learning, we have to do learning such that approximate inference works well. And that changes the whole game. OK, that's it.
So I don't know if you have a break in your day at tea time.